So the reason why elements form most common ions is pretty much because having incomplete shells make them unstable, right? It's just like you want to be complete or you are an unstable person, right? And so they like to fill up their shells either by losing their valence electrons or gaining more valence electrons, basically becoming an ion. And that's what we call a most common ion. I'm going to show you guys how we can use these shell models to prove, hey, what's up? What an element's most common ion is going to be. So let's start with sodium. So I'm going to give you guys about a minute. I want you guys to draw sodium's shell model. Okay, so draw sodium's shell model on your paper. And then after that, we will talk about how it loses electrons to become an ion. All right, guys, so let's take a look at sodium's shell model. So we got sodium right here. To do it, you first need to find the shells. So look at sodium. It's in the third row of the periodic table, right? So it's going to have 3 shells. And in the first shell, the first row of the periodic table has 2 boxes. So there are 2 valence electrons in the first shell. Second shell, there's 8 boxes, so 8 valence electrons. And sodium is the first box in the third row, so it has 1 valence electron. Everybody cool with the shell model? Just count the boxes and the rows. All right, now, we're going to look at why sodium wants to become +1. If you guys take a look right here in the valence shell, there's 1 valence electron, right? But what's the maximum number of electrons that can be in sodium's valence shell? Yeah, it can have a maximum of 8, okay, because there's 8 boxes in the third row. Okay, now, when we look at it, it has 1. The maximum it takes to fill it up is 8. That means sodium pretty much has 2 options in order to form its ion. It could either lose 1 electron, or it can gain 7 electrons, right? It could lose this one to empty the shell and get a complete valence shell on the inside, or it can fill up its shell. And if we just look at it in terms of numbers, pretty easy to tell it's going to be easier to lose 1 electron, right? And that's the reason why sodium wants to lose 1 electron, because if you lose that electron, that valence shell disappears, and the second shell becomes its new valence shell. Okay, and that's why sodium wants to become sodium +1. Okay, it's pretty much that reason. Okay. All right. I'm not gonna have you guys do oxygen just for the sake of time. I'm gonna just show you guys real quick. But oxygen, if we take a look, oxygen is on the second row of the periodic table, so it's gonna have 2 shells, 2 electrons in the first shell, 6 in the second shell. Same thing as sodium. It could either fill up the shell or lose, but here oxygen would have to lose 6 electrons or gain 2 electrons. And numerically, it just makes more sense to gain 2. And so that's why oxygen becomes 2-, because it wants to gain 2 electrons. So the shell model kind of helps us visualize why these elements want to become the ions they become. Okay. Any questions on that? Okay, we're just connecting shell models with most common ion. All right, let's move on. So we talked about the pattern, the +1, +2, +3, so we're not going to go over that. We're going to get into now the first new thing for this unit, and it's something called electronegativity. Okay, electronegativity. And very simply put, electronegativity is how tightly an element holds on to its electrons. Okay, so electronegativity is a measurement of how tightly an element holds on to its electrons. Okay, so this is the first main concept for today. So the first thing you want to look at when you're determining an element's electronegativity is first, what is its most common ion? Does it want to gain electrons or does it want to lose electrons? Right? Because electronegativity measures how tightly an element wants to hold on to the electrons. Well, if it wants to gain electrons, that means it's going to hold on to the other ones pretty tightly, right? So the electronegativity will be higher. Whereas if you're trying to get rid of electrons, the electronegativity will be pretty low. Okay, so that's the first factor. What is its most emphasized? Does it want to gain electrons or does it want to lose electrons? And if we kind of want to extrapolate that a little bit, if it wants to gain electrons, the electronegativity will be higher. But if it wants to lose electrons, the electronegativity will be lower. Okay, and En is just my way of shortening electronegativity. All right, the second factor, and these go in order of importance. Okay, so the most important thing is the most common ion. The second thing that's important is the number of shells, because that determines how far away the electrons are from the nucleus. And so, if we want to kind of expand on that a little bit, if you have more shells, right, that means the electrons are further away from the nucleus, right? And so if you have more shells, that means the electronegativity is going to be lower. So as you go down the periodic table, the electronegativity will typically get lower. All right, and then the last factor is going to be the number of protons that the element has. Because the more protons it has in the nucleus, the more positive it is, right? The more positive it is, basically the stronger positive magnet it is. So it's going to hold on to the electrons a little bit more tighter. So if we want to kind of bring that up too, if you increase the number of protons, typically the electronegativity will also increase. Okay. And so those are the factors that determine electronegativity. And pretty much what you're going to be doing for these types of problems is you're going to be either comparing how electronegative an element is compared to another one. There's also questions where I give you multiple elements and ions, and then you need to rank them in terms of electronegativity. But we'll kind of ease into that. There is a pattern that we can get out of this, and this is kind of a general pattern that helps you visualize it, but let's talk about the pattern. So let's say this is my periodic table. Okay, so if you have your periodic table, or let's say it looks like this, right? You have your periodic table. This is your periodic table. Now, as you go up and as you go to the right, it's going to become more electronegative. Okay, which makes sense, right? Because if you go up the periodic table, there's less shells as you go up, right? The ones higher up have fewer shells, which are more electronegative. And as you go to the right, there's more protons in the same row as you go to the right. So as you go up and right, it's going to become more electronegative. So this is a very easy pattern to just kind of remember, and it'll help you with most of the questions. Okay, there are a couple questions where you'll have to use this right here. So just make sure you still remember the 3 important factors for electronegativity. Okay, so first we're going to compare sodium and lithium. So let me pull up my periodic table. So sodium and lithium. I'm going to have the periodic table out just so that we can compare. So we got sodium and lithium right over here. Now, if we take a look, well, I'll give you the answer first. So the answer is lithium is more electronegative. And the reason why is because of the shells. It has fewer shells. Okay, if you wanted to get super in detail, you can say since it has fewer shells, that means that the valence electrons are closer to the nucleus, right? You can add that, but honestly, you can just say lithium has fewer shells, so it's closer. All right, let's go to B. Fluorine, we're looking at fluorine and beryllium, so F and Be. The answer is going to be F. F is more electronegative, and you would say that it has more protons. That's one answer. You can also say that fluorine, it wants to lose electrons. Okay, so either answer would be, or either justification would be fine. Okay, fluorine has 9 protons. They both have 2 shells. Beryllium has 4 protons, though, so the positive charge in the center is stronger for fluorine. Okay. All right, let's go to the next one. We are comparing nitrogen and sulfur, and for this one, the pattern kind of fails here because we said that the pattern is that as you go up and to the right, it's more electronegative, right? But they're exactly one square like diagonal from each other, and so it's kind of hard to tell with the pattern. So we have to use the information that we learned. The answer is going to be nitrogen. Nitrogen is more electronegative, and the reason why is because it has fewer shells. Okay, and so that is going to be our answer. Okay, sulfur has more protons, it's true, but sulfur also has 3 shells. So the electrons are further away, and that is going to make it less electronegative than nitrogen, which is 2 shells. Yeah.
So fluorine wants to do that.
Thank you. Wants to gain electrons. My bad. English is hard. Wants to gain electrons. My fault. Thank you. Sorry, guys. English, my second language.
You can say that.
I use the same jokes every year.
I was waiting for you to say it.
Okay. There's not that much unique information about it. That's all I can say. All right. Any questions about electronegativity? Pretty simple, right? So these are pretty simple when you're just comparing one element with another one. Where it gets a little bit trickier is when you start comparing multiple and you're asked to rank them in order in terms of electronegativity. So I'm actually going to go over how to do this with you, and then after that I'm going to have you guys try it on your own. So the first thing you want to look at, or when you're ranking these in terms of electronegativity, is you just want to gather as much information as you can about these elements. Okay. The first thing you want to pretty much write down is you want to look at the shells, and then after that you're going to look at the protons. So for each of these 5 elements, I want you guys to just real quick jot down how many shells and how many protons does it have. Okay, and after that I'll show you guys how to finish up the problem and rank them in order of electronegativity. Alright guys, so I have these shells and the protons up there for you. Okay, and so first thing you want to do is you just want to get that information, and then from there we're going to start ranking it. So it says to rank from least to greatest electronegativity, so we're going to start with the one that is the least electronegative, and then we're going to go up to the one that has the most electronegativity. Okay? Okay, if you want to go the other way, you can just start on the right side and then go left, or go left to right. Doesn't really matter. Okay? So let's take a look at the shells first. Now the shells are going to determine which one is the least electronegative. We said more shells means less electronegative. Yttrium has the most shells, so yttrium is going to be the least electronegative. And we're done with this. Okay. Makes it pretty simple. It's just 5. It's the one that is the outlier. It has the most shells. Okay, next, we're going to have to look at the one with the next most, and it's either going to be phosphorus or chlorine, right? Because they both have 3. Okay, for this, we have to look at the protons. Now, between the two, chlorine has more protons, and if it's more protons, that means it's more electronegative in the same row. That means phosphorus is going to be less electronegative than chlorine. Okay, so we're done with that one right there. And I'm going to give you guys 30 seconds. See if you can do the last 2 based on how we're doing it. Put the last 2 in order. Alright, and then for the last one, we're going to be looking at nitrogen and fluorine. Fluorine has more protons, so it'll be NF. And this will be your order from least to most electronegative. Alright, any questions? That's electronegativity. That's about as hard as it's going to get. Okay. Alright, now, one quick thing before we move on. There are numbers that go with electronegativity. So before we move on, I do want to show you this chart. You don't need to memorize it or anything, but just so that you're familiar with it and you're able to interpret it. There are values for electronegativity. Okay, the most electronegative element is fluorine. Okay, the noble gases, we actually don't give them electronegativity values because they're already complete valence shells, so they don't want to gain or lose. So they're not even in the conversation. So fluorine is the most electronegative with a value of 4, and then as the numbers go down, that just means that they are less and less electronegative. Okay, and then the least electronegative is going to be francium right here with 0.7. Okay, so if they talk about electronegativity values for whatever reason, or they give you this table, that's how you interpret it. Okay, the higher the number, the more electronegative that element is going to be. All right, so the next thing we're going to talk about is something called atomic size, and that's exactly what it sounds like. It's how big an atom is. Another term that might be used for this is the atomic radius, which is pretty much the same thing. If you remember from geometry, radius is the distance from the center of a circle to the end, just halfway through, and that basically just measures size, right? Because atoms are spherical, And so radius is another way to just talk about size. So either term is just talking about how big is the atom. All right, now there are three factors that affect atomic radius, and they go in terms of importance again. The first most important thing is probably pretty obvious. It's the number of shells. More shells means bigger, right? So more shells is bigger because the more shells there are, the greater the distance from the nucleus. So if we wanted to kind of summarize that, it would be as you increase the number of shells, you're going to increase, and I'm going to write AS for atomic size. All right, let's move on to the next most important thing. It's going to be the number of protons. Now, we know that protons and electrons are attracted to each other, right? So if they're attracted, they pull each other closer together, which is going to shrink the size of the atom. So the more protons there are, the smaller the atom is going to be. Okay, so the more protons there are, the more it's going to shrink the atom. Now, shells is more important. So don't be like, Mr. Barium has more protons than hydrogen, so it should be smaller. No, the shells are the most important thing. And when you're in the same row, the protons are going to make the atom smaller. Yeah.
So like sodium at a higher size. Phosphorus.
Yes, correct. Mm-hmm. Yeah, same row. And then the last thing, electrons. This is the least most important thing. And for this one, electrons push each other away, which makes the atom bigger. And so if you increase the amount of electrons, it will increase the atomic size. Mm-hmm. Okay, so there's a pattern for this as well, and it's actually the exact opposite of electronegativity. So if you have your periodic table, that is very asymmetrical, but if you have your periodic table, as you go to the left and as you go down, it's going to get bigger. Okay. All right, so let me give you guys about 2 minutes. See if you guys can do A and B for number 9. You're just picking which one is bigger, and just write a short explanation. Why is your choice bigger?
You're good at you don't have nothing.
All right, guys, let's go over 9. So beryllium and barium. So if we look at the periodic table, this one's pretty easy, right? Beryllium is second row, 2 shells. Barium is sixth row, 6 shells. So your answer is pretty easy. The bigger one is going to be barium, and you would say more shells. Okay. And even if we drew this on a piece of paper, we would see it. Beryllium has 2 shells. Barium has 1, 2, 3, 4. Yeah, you can kind of just see that it's going to be bigger. All right, the next one is going to be phosphorus versus sulfur. And this one's a little bit trickier because they're in the same row. They both have 3 shells. However, the smaller one, wait, do we say smaller or bigger? Bigger. The bigger one is going to be phosphorus, and it would be because they both have 3 shells, okay, but phosphorus has less protons, okay, less protons, and so there is less attraction to the nucleus. Okay, and so that's the reason why. Okay, easy peasy. All right, any questions on 9? Chillin'? Okay. Just so you guys know, these ranking questions, you will have them on your exam for sure. Okay. All right, so let's go to the next problem. We're gonna jump down to 11, and there's gonna be a bit of a difficulty jump here, and the reason why is because not only are we gonna be asked to rank them in terms of size for neutral elements, you're also going to be asked to rank the size for ions as well, and that's where things can get a little bit weird. But if we follow the methodology that we've been using, it's not too bad. Okay, so what I want you guys to do is I'm going to give you guys about 3 minutes. I want you guys to, same thing as before, determine the number of different things for each of these atoms. First, I want you to determine how many shells does it have, then how many protons does it have, and then how many electrons does it have. So 3 things for each atom. You're going to be looking at hydrogen, hydrogen's most common ion, potassium, potassium's most common ion, bromine, and bromine's most common ion. So find the shells, protons, electrons for all of them, and then I'll go over how to rank them from smallest to largest. Alright, so I got the shells for the neutral elements up there for you guys, and also the protons for all of them, right? Because it doesn't matter if it's an ion or neutral, the protons never change. Okay, so let's go to the electrons for the neutral one. So for neutral elements, the electrons are going to be the same, right? So it's going to be 1 and 1 for hydrogen. Potassium is going to be 19 and 19. Bromine is going to be 35 and 35. Now, the most common ions are going to affect the electrons first, so let's start with that. So what is hydrogen's most common ion? +1, yeah, it's +1, okay, it got scared there. +1, that means it loses an electron, so it goes from 1 to 0. Okay, potassium, what's potassium's most common ion?
+1.
+1 as well, so it's going to lose an electron, so it's going to go from 19 to 18. And bromine is -1, so it's going to go from 35 to 36. Okay. All right. Now we got to look at the shells because this is where things can get a little bit tricky. So let's start with hydrogen. Regular hydrogen has 1 shell and 1 electron. So if we go to H+, you lose an electron. So we have 0 electrons. So if you have no electrons, how many shells do you have? Yeah, no shells. So automatically we can see this is going to be our smallest element. H+ will be our smallest. So we are ranking them from smallest to largest. So we have our first answer is going to be H+. And we are done with that first one. Okay. Let's go to potassium now. If we take a look at potassium, it typically has 4 shells. So K has 1, 2, 3, 4 shells. Now, if we take a look at K, how many valence electrons does it have? How many?
1.
1. It has 1 valence electron because it's the first box in that 4th row. So when we go to K+, that means we're going to lose that electron in the valence shell. So what happens to that outside shell?
We have 8.
Yeah, it disappears. And so, yeah, we're going to have 8 valence because now K+ is going to have 3 shells with 8 valence electrons. So the 3rd shell, one of the inner shells, becomes the new outer shell. And so K loses a shell. So K+ actually has 3 shells. Okay, so that's one of the tricks for this question, is identifying potassium. It's going to lose its valence shell. And then for bromine's MCI, if we draw bromine, I'll do the Lewis structure for this one. Bromine has 7 valence electrons. It gains an electron to become Br-, which means it just fills up its valence shell. So this is still going to have 4 shells. Okay, so bromine still has the same number of shells, but potassium is actually going to lose one of its shells. All right, so in terms of the ranking, it's pretty simple from here. Let's go from H+. H+ had 0 shells. Which one is the next smallest?
1.
Yeah, 1, hydrogen, because it has 1 shell. So that's going to be our next. Okay, which one is the next smallest? 3, potassium's most common ion. Good. So K+. Okay, now the remainder of them have the same number of shells. It's 4, so we can't look at the shells. So we move on to the protons. Okay, now we said that more protons means what? Bigger or smaller? Smaller. More protons means smaller because it's pulling the electrons more. So we get an answer here. Potassium is going to be our largest. Okay, so there's a big gap between potassium and potassium plus. Okay, so we got 2 slots left over for Br and Br minus. Okay, Br and Br minus have the same number of protons, so we got to look at the electrons. Now, we said that for electrons, the more electrons it has, does it get bigger or smaller? Bigger, yeah, because the electrons push each other away. That means Br minus is going to be bigger than Br, and that is our ranking. Okay, so a little bit tricky, right, with the ions, but just keep that in mind. Always find the shells, protons, and electrons, and you should be good. So the next topic is what we talked about before. It's about something called ionization energy. Okay, and if you guys remember, ionization energy is the amount of energy required to remove an electron from the atom. Okay, there is a more technical definition, but just think of it as how much energy you need to put in to take an electron out. Okay. Okay, I abbreviate ionization energy as IE. So just if I write IE, just know it means ionization energy. Now, there are different types of ionization energy. There's numbers that go along with it. So, for example, right here, this is the IE1, first ionization energy, because it is the amount of energy required to remove the first electron from sodium. Okay. But then every time you remove an electron, there is a different ionization energy. So the second ionization energy, we're going to call that IE2. Okay. So it's the amount of energy required to remove the second electron. So I'm going to draw what that looks like here. You guys don't need to draw this picture. This is more for a visual for you. But typically, sodium is going to have 3 shells, right? And sodium has 1 valence electron. Okay. So IE1, the first ionization energy, is basically the energy required to remove this first electron. So I'm going to draw an arrow with an electron leaving. Okay, and so it's the energy required to turn sodium into Na+, where it has 2 shells. Okay, and then it'll have 8 valence electrons because it lost a shell. But does that make sense, guys, what IE1 is? It's just energy required to remove that first electron. Okay, IE2 would be the energy required to remove another electron from the sodium. So it's taking Na+ to Na+2. That's the second ionization energy. So every successive ionization energy is just how much energy do you need to remove another electron, and then another one, and then another one, and so on and so forth. Okay, so it's basically the energy required to do this. Okay. And then I'm not going to draw the other ones or write it down, but there's going to be an IE3, which is to take Na to 3+, and so on and so forth. Okay. All right, now ionization energy, there's a couple things that we need to talk about it. It is closely related to electronegativity. Hold up, sorry guys, my pen is not working. So ionization energy, it is closely related to electronegativity, right? Because we said electronegativity is, it talks about how tightly the electrons are being held, right? So obviously ionization energy, the amount of energy required to remove an electron, that is going to be tightly or closely related to how tightly the electronegativity is. So the trend is the more electronegative an element is, the higher the ionization energy, which makes sense, right? If I'm holding onto an electron really tightly, it's going to take a lot of energy to remove that electron. So that is the relationship between ionization energy and electronegativity. The more tightly that electron is being held, the more electronegative it is, the higher the ionization energy.
What did you say?
All right, so with that being said, let's have you guys try a couple on your own. So we're going to be comparing which one has the smaller ionization energy between these elements. So if you guys recall, smaller ionization energy basically means that it is easier to remove the first electron. Okay, and so it has to do with electronegativity. So think about electronegativity. Think about most common ions. But I'm going to give you guys a couple minutes to try A, B, C, D, and E, and then we'll go over it. Pick your answer. Same thing as before. Write a little explanation after your answer, describing why you chose your answer.
When do you get Noah?
For Chris.
When do you get Sam?
Bro, you do this. What do you
I did do it. I did it all in my head. I went.
CL or
First one's actually pretty hard.
Is it? Wait, I was there.
I think it's the hardest one.
How's the first one? Yo, what are we doing? Okay.
All right, guys, just another minute, and then we'll start going over it together. You know where it is. I'm basically Walter White. I'm supplying her with drugs.
you can just
I don't know what you're talking about. I don't know you're taking it. Oh shoot, that was all being recorded. Oops.
And the best part is
Yeah.
I forget to
Yeah.
take it out.
I know. I just don't care enough. Okay, let's start going over it, guys. So we're gonna start by comparing chlorine and argon for the ionization energy. So it helps to look at the periodic table. So we're gonna look at the periodic table to do it. Okay, so we got chlorine and argon, and this is actually, I think, pretty tricky. Okay, if we take a look at their let's take a look at their Lewis structures. Okay, chlorine. How many valence electrons does chlorine have? 7. Yeah. 1, 2, 3, 4, 5, 6, 7. So it's gonna have 7. How many valence electrons does argon have? 8. Okay. All right. So that is the Lewis structure. So let's talk about a couple things about these two elements. Now, if you take a look at chlorine, what we know about chlorine is that chlorine wants to gain 1 electron, right? Because it wants to become Cl-. Argon has a complete valence shell, so it is it's neutral and it doesn't want to react with anything because it has a complete shell. So argon is stable. That's a characteristic of all the noble gases in this column. They have complete valence shell, so they don't want to gain or lose. So if we're comparing which one is easier to take an electron from, I'm just going to give you the answer, and I'll explain why. But the answer is going to be chlorine. Chlorine has a lower IE1. Okay, now you might be wondering, hey, Mr. O, but it wants to gain an electron. Wouldn't it make more sense to be harder to take an electron from this? That's a great point. But there's a couple things that we need to keep in mind. So argon, since it's already stable, it's holding on to it really tightly. So since it's already complete, it really does not want to lose an electron. So the already being stable already makes it so that it's even harder to take an electron. So the stability is going to increase the first ionization energy. Okay? Another aspect that we need to think about is the number of protons. If you look at argon, it has more protons than chlorine does, right? So since it has more protons, there is a stronger, there's a stronger pull into the nucleus. Okay, so since the nucleus is pulling the electrons tighter, it is harder to remove electrons for argon than chlorine since it has less electrons. So the answer for the first one is going to be chlorine. Okay. So that is the first one. I think that's probably one of the harder ones. Okay, so it is easier to take an electron from chlorine than it is from argon. All right, everybody good with that one, with A? Okay, let's go to part B now. For part B, we are comparing beryllium and we are comparing calcium. So again, we're looking for which one is easier to remove an electron from. The answer is going to be calcium. Calcium has a lower IE1, and the reason why is because it has more shells, right? More shells means increased distance from the nucleus, and so it is easier to remove. What's up?
You need a TA for the test?
No, I actually can't. Yeah, unfortunately. I have like 4 in this class already.
Damn.
Okay, make sense? More shells, further away, easier to remove. Okay, let's move on to the next one. Next one we are comparing potassium and cobalt. Now, they both have 4 shells, 4 shells. So K and CO, they both have 4 shells. Okay, so what do we need to look at in order to determine their ionization energy? Protons. Great. Okay, nice. So, which one has, which one has fewer protons? Because that makes it easier. Yeah, K has fewer protons, and so K is going to be your answer. K has a lower ionization energy because since it has less protons, same thing as before, it has less attraction to the nucleus, so it's easier to remove that electron. All right, next one is we're comparing sulfur and germanium. So we got sulfur and germanium right here. What's up? Uh-huh. It has 4 because it still has electrons in the 4s subshell, but it ends on the 3d subshell for the counting. Yeah, great question. Yeah, so 3d is the highest energy level, but still has that 4. Yeah. Okay, germanium and sulfur. Anyone want to take a shot at it?
Germanium.
Okay, why do you say germanium?
4 shells.
4 shells, exactly. Yeah, more shells, so it is easier to remove. Right. And then the last one, we have tin, SN, and tellurium, TE. Which one is easier to remove? Tin. Why tin? Less protons. Great. And that's it. That's how you compare ionization energy. It's pretty much the same thing as electronegativity for now. Okay, so ionization energy is, again, the same thing as electronegativity when we are looking at the first ionization energy. Okay, however, the AP test likes to mess with you guys, and they don't ask a lot about first ionization energy. They ask a lot about the successive ionization energy. So we are going to look at a problem that has to do with that. So for 813, we are going to talk about what has a greater third ionization energy, calcium or sulfur. Now, in order to do this, we need to, I think it helps a lot to draw it out. So we're going to draw this one out, okay? So we're going to draw out calcium and sulfur. What we're going to do, just to make it easy, let's do the Lewis structure. Okay, so we got Ca and we have S. I'm going to give you guys 30 seconds. Draw the Lewis structure for Ca and S, and then we'll talk about the ionization energy stuff. All right, guys, so for calcium, it's the second box in that row, so it has 2 valence electrons. And then S, it's going to have 6. Okay, so far so good? Okay, let's go to their ionization energy. So let's start with calcium. So when you remove an electron from calcium, so i.e. 1, it becomes Ca plus, and it has 1 valence electron. Okay? If we do i.e. 2, we are removing that second electron, so it's going to become its most common ion, Ca2 plus. And it's going to end up with 8 valence electrons because it's going to lose its valence shell. All right, and then the third ionization energy is you're basically breaking that stable complete shell. You're turning it into Ca3 plus, and you're going to end up with 7 valence electrons. Okay, so that's IE3. So we are looking at, is calcium's IE3 going to be greater or sulfur? So we got to look at what happens when you do sulfur. Okay, so let's draw what happens to sulfur when you do IE3. So first ionization energy, you're removing an electron, so it's going to become S plus. Okay, and it's going to have 5 valence electrons. Okay, IE2, you're going to become S2 plus, and you're going to have 4 valence electrons. And then we go to IE3, it's going to become S3 plus, and it's going to have 3 valence electrons. Okay, so we are going to be comparing the IE3s. Now, the reason why this is tricky is because a lot of times people see ionization energy and they look at calcium and say calcium wants to lose electrons, so it's going to have a lower ionization energy than sulfur. Sulfur wants to gain. Okay, but that's not what we're looking at. We're looking at the third ionization energy, and so we're comparing this step right here, taking away an electron. Now, based on what we've learned, anyone want to take a guess which one has a greater ionization energy?
Calcium.
Yeah, calcium does. Why?
Because it takes more energy to break the stable.
Exactly, that's the answer. So the answer is going to be calcium, and your reasoning will be, there's actually a couple. The first reason is because you're breaking a stable shell. Okay, and we talked about how breaking a stable shell requires a huge amount of energy. If you look at sulfur, it's not complete yet, and as we lose more, it becomes more and more unstable, and so it's easier to break something that's unstable than somebody that is stable, right? So breaking a stable shell requires more energy. Okay, the second reason why is because it's about the number of shells. If you look at calcium 2 plus and S2 plus, they both have 3 shells. Okay. Okay, calcium I know is in the 4th row, but it lost the 4th shell, so they have 3 shells. Okay, but calcium has more protons. So calcium, because it has more protons, same number of shells, it's pulling the electrons more tightly. So since it's holding the electrons more tightly, it's harder to remove that 3rd electron from calcium. Those are the 2 main reasons why. All right, so we're going to continue talking about ionization energy, and for this problem, we're going to look at a chart that tells you the ionization energy of different elements as you go through the successive ionization energy. So I'm just going to give you the answer for this. You guys don't need to write it down, but actually I would recommend writing it down. Never mind. So what you guys should see in this chart is that each column or each row has a different element. Each column is the first ionization, second ionization, third ionization, so on and so forth. Now, this blue section right here is going to tell you when you go into an inner shell. So for example, sodium, once you take away an electron, it becomes Na2 Na plus, right? And in order to remove the second electron, it takes a lot more energy, right? And we've talked about this, because once it loses an electron, it gets a stable shell, and breaking that stable shell is extremely difficult. Okay, and getting even further into the ionization energy, it gets even harder, and that's why there's no value for these even. Okay, so that's what you guys should identify for these elements. Okay, what you should identify is that as you start going deeper into the ionization energy, removing electrons from the inner shells becomes extremely, extremely difficult. There's a big jump. Okay, so we're going to jot that down right here. Okay, so the first trend you should identify is that removing inner shell electrons requires a lot of energy. Okay, so that's the first thing you should identify here. Okay, so removing inner shell electrons requires a lot of energy. Okay, and then so the question is asking about magnesium and chlorine. And so if you look at magnesium, Mg, the most common ion is Mg2+, right? And that's when you get into the inner shell. And if you notice, there's a huge jump going from the second ionization to the third ionization. Mg wants to lose the first two electrons, so it's pretty easy. And then it gets really difficult after that. Okay, whereas if you look at chlorine right here, chlorine is just kind of steadily goes up. There's no extremely large jump in terms of losing the or in terms of the ionization energy. Obviously, as you get further and further in, as you start taking away more electrons, there are more protons and less electron repulsion. So it does end up getting pretty high, but there's no really big jump in energy. It trends pretty linearly. Okay, so that's what you should identify about these ionization energies. Keep that in mind. The big takeaway from this is removing inner shell electrons, extremely difficult. All right, let's move on. Oh God, I forgot about this. Okay, we're going to talk about something about PES. So in order to do this, I'm actually going to go into a different document. This is a lab technique that they might ask you about on the AP test. So it's called photoelectron spectroscopy. Photoelectron spectroscopy. I totally forgot this was even here.
Just don't even teach it.
It's going to be on your test, though. Yes. No. Okay. So photoelectron spectroscopy. Basically, what this allows us to do is, basically what it does, I'll show you what it is. It gives you a graph that looks like this. It's not that bad, guys. So when we take a look at the graph, what each of these peaks tells us, it tells us how many electrons are in each shell and each subshell. Okay? So it's actually not that difficult to interpret. It tells you how many electrons are in each shell and subshell. So we're going to go through each element because I think that's just the easiest way to identify it. So if you look at hydrogen, the electron configuration for hydrogen is 1s1, right? So it has one electron in the 1s subshell. And so hydrogen will have just one peak in its PES. Pretty easy to understand, right?
Yes.
Okay. Now keep the height of this peak in mind as we go on to the next element. The next element is helium. Helium, the electron configuration is 1s2. It has 2 electrons in the 1s subshell. So if you look, it's going to have one peak. This peak is going to represent the 1s subshell. Now, I said keep an eye on the peaks because if you look at helium's peak versus hydrogen's, what do you notice? Yeah, it's pretty much double, right? Which makes sense because helium has 2 in the 1s, hydrogen has 1 in the 1s. Okay, so the height of the peak tells you how many electrons there are going to be. Okay, everybody good? Okay, so we can kind of think about lithium next. Lithium, the electron configuration is 1s2, 2s1. So this is the 1s subshell, and if you look, the peak is double the height of this one, which represents the 2s subshell, where there is 1 electron. Okay, so every time you go to a new subshell, there's a new peak. So this is the 1s, and this is the 2s, but the height of the peak depends on how many electrons there are. So if we were going to talk about beryllium next, okay, what change would we make to this chart for beryllium? Yeah, double the second peak, right? Because it has 2 electrons in the 2s. And so if we look at beryllium, that is exactly what we see. The peak is about the same as the 1s peak. Okay. Now, when we go to the 2p, this is where we get a little bit of a change. Let's go to the next one, boron. Boron has 3 peaks. Okay, this is the 1s subshell. This one is the 2s subshell. This is the 2p subshell. Okay, boron is 1s2, 2s2, 2p1. And so you guys kind of see that same pattern, right? Peaks for each subshell, and the height is determined by the number of electrons. That's what PES is. It's this. Now, one thing you should note is that there is a big distance between 1 and 2, right? The shells. But between the subshells, they're kind of clustered together because the subshells are still around the same energy level. Okay. All right, if we go to the next element, carbon, what change should we expect on the next one?
The third peak will double.
Exactly. Third peak will double because there's another electron in there. So let's take a look at carbon. It's exactly what we see. If we move on to the next one, nitrogen, what difference should we see in nitrogen? Yeah. Not triple, but it's going to go up another unit. And so, yeah, the third one gets a little taller. The next one, oxygen, has 4 in the P subshell, so you're going to expect, yeah, it gets even taller. And then you guys kind of see the pattern. Fluorine gets taller, neon gets taller. Okay. The last, no, I think, I don't think we even have the PS data for that, or I don't have it here. Okay, so let's go to the next one, sodium. What difference do you think you'll see in neon and sodium?
There will be another peak.
Yep. Another peak, but tell me about the peak. What, like how close, how far?
It should be far.
Should be far, and what about the height? Yeah, small. It should be just go up to the 1, about half of the S ones, right? And so if we take a look, it's exactly what we see. And so that's PES. That's the data that it gives you. It tells you, if you guys want to jot it down in your notes, what PES tells you, it gives you a peak for each subshell. Okay, that's the first thing. The peak height, okay, it's correlated to the number of electrons that are in that subshell. Okay. The shells, the peaks that represent each shell are far, but the subshells in the same shell are going to be close. Those are like the 3 main things that you'll have to know about PES data. Okay, each peak represents a subshell. The height of the peak tells you how many electrons there are relative to the other peaks, and then the distances is dependent on the shells and the subshells. Subshells are close, shells are far away. So look right here. This is your graph. What element do you think this PES spectrum is representing? Don't say it out loud. Just write it on your paper and write a quick, very small justification why. Why do you think your answer is represented by this PES spectrum? Okay, guys, let's go over this. So let me just talk about what each peak represents, and then we'll talk about what element at the very end. So the first peak represents the 1s subshell, and then we got a long gap, so now we're at 2. This is the 2s subshell. This is the 2p subshell. Everybody good with that? Okay, so there are 3 peaks, and we're going to end at an element in the 2p block. So we know that 1s has to fill up with 2. Go to 2s, it's the same height, so that means it's 1s2, 2s2, and that means that if you look at this graph, each bar, so 2 bars represents pretty much 1 electron, right? So that's 1 electron, 2 electron, this is 1 electron, 2 electrons. So that is going to help us figure out how many electrons are in the 3rd subshell. If we count, it's 1, 2, and 3. So that means it's going to be 2p3. So if we look at the periodic table, 2p3 is going to be nitrogen, and that's going to be your answer. Okay. So first thing you want to identify, how many peaks? Then you identify what's the height of the peak. Using 1s and 2s, you can determine that there are 3 and 2p, and that gets you to nitrogen.